Okay, here we go with a couple of help things for chapter 18 and 19, number 2 and number 5. So chapter 18, 19, number 2 and 5. Okay, number 2 is a problem where you start with a strong base, you're given the pH, and you're asked to find how many moles of hydrogen ion or hydroxide to change it to 8.67. Now, if the pH is going down, pH is decreasing, that means that the solution is getting more acidic. That means to change from to change that beaker of base to something more acidic, you're going to need to add hydrogen ions. Okay, so that answers that question. Now, the pH is changing by 9.87 from 9.87. Okay, so we know the pH, but what we want to do is we want to figure out how much does the hydroxide change so that we know how many moles of hydrogen to add. Okay, so we start at pH 9.87 and we want to go to 8.67. So that means that the pOH for that solution is 4.13. Over here, the pOH is 5.33. Okay, don't forget these have to add up to 14. Okay, so if the pOH is 4.13, then the OH concentration is 10 to the minus 4.13. Likewise, over here, and you know how to do that in your calculator. So you get 7.4 times 10 to the minus 5 moles per liter. And over here you get 4.68 times 10 to the minus 6 moles per liter. Now that gives us a change of this much. All right? And if we want to know how many moles of hydroxide that changed, then we need to get rid of the liters. Well, we know that we had 98.5 milliliters, so that's 0.0985 liters, and that gives you an answer of moles. Okay? So how do you know how to answer this question? Well, you're asked to calculate how many moles. So you know that you've got to end up with moles here. Okay? And the only thing you've got to go from is the pH. Well, pH can be converted to OH concentration and H concentration. I think you could probably approach this from the hydrogen ion concentration, but I'm not sure. I didn't do it that way. Okay. Number 5, a little more involved. And in number 5, you have a salt solution. You have a salt solution. Okay, now, if you don't know what that means, and if you don't know how to calculate whether it's an acid or base solution, then you might want to go back to one of those videos in the modules. So let's just look at this. The K comes from a strong base, okay? And that means that this has no acid-base properties whatsoever, okay? And, okay, because remember that the stronger the base or the acid, the weaker its conjugate, okay? So no acid-base properties. And the fluoride comes from HF. Now, that's a weak acid. You know why it's a weak acid? Because it's not a strong acid. There's a list of 6 of them. Everything else is weak. So if that's a weak acid, that means that, let's give this, that means that this, let's go, this has some acid-base properties, all right? Okay, so this is what's going to determine the acid-base properties. That's a base, okay? If this is an acid, its conjugate is a base. If this is a base, then that's the conjugate acid, okay? So we know it's a base. That means that to calculate this problem, we're going to need the Kb. But you were given the Ka in that problem. Well, Kb, don't forget, is Kw divided by Ka, okay? Because these two things times each other give you Kw. So Kw divide by the Ka, Kb is 1.4 times 10 to the minus 11. Okay, so we've got our Kb. And to get the pH, we need to know the hydrogen ion concentration. Well, let's start with this, all right? We know it's a basic solution. Now, going back to the video I sent you, it's a basic solution. If it's basic, we must start with this expression for our balanced equation. You must start there, all right? And we know that this is going to be our base here, okay? So if this is a base, this is an acid. If this is an acid, its conjugate is a base, and that means that this base must have a conjugate acid, and that, of course, is HF, all right? In my opinion, one of the hardest things about acid-base problems are, what is this equation? Because if you don't know what that equation is, you can't do the ICE table. You don't know where to start. So don't forget, if you have a basic solution, you're going to write this down first, all right? Now, we know that the KF solution is 0.6 moles to begin with. Initially, 0.6. Initially, the water is something. We don't care. It doesn't have a molarity. Initially, this is 0 and 0. It's going to change by some amount called x. This is going to go down by x. But over here are products, and this is going to go up by x, and this is going to go up by x. How do we know it's x and not 2x? Because this is a 1, this is a 1, this is a 1, this is a 1. If this was a 2, this would be a 2x. But it's not, okay? And I'm not going to give you any problems like that. Okay, so at equilibrium then, okay, to end up with, and remember, in an ICE table, we use molarity. BCA chart moles, ICE table, molarity. Because BCA tables are about chemical reactions, and chemical reactions are about stoichiometry, and stoichiometry is about moles, okay? ICE tables are about equilibriums, and equilibriums are measured with molarities. Okay, so at equilibrium then, we're going to have x and x, all right? So we're doing pretty well. We've got our Kb is 1.4 times 10 to the minus 11. X times x, products over reactants. And this number is really, really small, so that means that we don't need to worry about this. X is not going to change very much, okay? Or X is not going to change 0.6 very much. All right, so X then, as you do the math, is 2.9 times 10 to the minus 6. And if you take the negative log of that, okay, because that is your hydrogen ion concentration. Okay, if you take the negative log of that, you get not the pH, you get the pOH. And boy, a lot of you figured out the pOH and reported it as the pH. But look up here, okay? You calculated the OH, and the reason that you probably got a little confused on that was, as I said before, if you can't write that equation and know that it's a basic solution, you're not going to have that OH there. You're going to have an H instead, so be careful. Okay, so the pOH is 5.54, and that means that the pH is 8.46, and that is your answer.